All right, so welcome to Unit 5, Activation Functions. All right, this is Unit 5. We are going to be talking about different activation functions. We've been using tanh, but we're going to find out there are some recent activation functions that are perhaps preferable. So we'll start with the vanishing gradient problem, okay? So when we talked about gradient descent, we saw that our update rule looked like this, or like this, right? Where D is the desired behavior, M, or equivalently f of y, right, is the output of the model, which is the activation function f applied to the pre-input y, right? And the pre-input, we remember, is the weight times the input plus the bias, right? And that blue might be really hard to read. Is that going to be a better color? Good, yes. So pre-input y is what we get by applying the weights to the input and then adding the bias, right? D is the desired behavior, and M is f of y is the model output, right? And f is the activation function, and y is pre-input. So this update rule intuitively makes sense, right? And again, remember that this is for the mean squared error. And if we use a different activation function, right, this is because of the mean squared error. And if we use a different if we use a different loss, this part might look different, right? So cross entropy, for instance, would have a different thing right here. But let's not worry about that for the time being, because the derivative of mean squared error is nice and interpretable, right? So desired output minus model output makes a lot of sense as an error term, okay? We are going to see that this f prime right here is a problem. All right? We're going to sort of refer to this as our error signal or gradient, right? All the stuff over here, we are going to call our error signal or gradient, and we're going to see that this term is going to be an issue. So let's look at tanh, which is the activation function we've been using, right? So before, where I write f of y, f is tanh, right? And tanh looks like this. It's sort of an S-shaped curve that asymptotically approaches -1 at negative infinity and +1 at positive infinity. Okay? And the gradient, which is f prime, right? Oh, that shouldn't. Looks like this. And I know that calculus was a long time ago for some of us. Remember that the gradient is steep, right? Or the gradient is high where the function is steep, and the gradient is 0 where the function is flat, right? So the gradient of tanh is near 1 around 0 where the tanh function is very steep, right? But then the gradient of tanh goes down to 0 out here where the tanh function starts being flat, right? So where tanh is flat, the gradient is very small, approaching 0. Okay? Cat. No. I have a cat that has decided it's mealtime. She's wrong. Now it's a battle of wills. So the problem is when we have to plug that f prime of y to get our error, right? So this is a little demonstration, right? Where blue is the desired desired behavior, and orange is the model behavior. Okay? So we wanted to get 0, right? We wanted to get 0 output here for whatever our input was. But what our model actually did was output 1, right? Because the pre-input was 4, right? So whatever our weights and biases were, whatever our inputs, weights, and biases were, we don't care. We know that our pre-input was 4, and so f of y is tan h of 4 is 1, okay? And our desired behavior was 0. So we first off look at this part, right? So we maybe look at this thing right here. I've written this down over here. Desired was 0. Model was close to 1. Tan h of 4 is close to 1, right? So that bit is 0 minus 1, negative sign is just 1, right? Negative 0 minus 1 is just 1. So our error, like the error part of our gradient here, makes a lot of sense, right? But we come over here and look at this f prime bit. So we know that y is 4. F prime, right, derivative of tangent, is 1 minus tan h squared. Oh, that's unreadable, isn't it? It's fun with picking pen colors, right? So f prime, or tan h prime, is 1 minus tan h squared. So if we plug in 4, remember that I just told you that tan h of 4 is very close to 1, right? So our derivative is 1 minus 1 squared, or something very close to it, which is 1 minus 1, which is 0. So again, and if you plug this into a calculator, right, 1 minus tan h of 4 squared, you get this. So we multiply, right? So we multiply our d minus m term times our gradient term times whatever our x was, and we don't really care, and we get something really tiny, right? 0.00134x. We say, whoa, wait a minute. What just happened, right? Because our error is pretty significant, right? We've landed in the saturating region of tan h, so our error is about as big as we could want it to be, right? We're near the maximum output of tan h, and we wanted 0. But our error ends up being tiny because we had to multiply it by this, right? This f prime term that was very, very close to 0 because we're out in the very flat saturated region. So that multiplication by f prime kind of swallowed or dampened our error term out. And indeed, we can so that was, to be clear, that analysis was if the error was 4. But we can kind of look at what happens as the error moves, right? So I really wanted to animate this. I really wanted to get a little thing where this line moves this way and you kind of watch the error go up and down. I couldn't make that work in time, but here is a graph, right? So this is a graph of that equation, right here. This is a graph of minus d times f of y, and that's the error term. Remember, that's d minus m, which is the error term, times f gradient of y, okay? And again, remember that is y the pre-activation, not x the input, right? That's y the pre-activation, okay? And so what we're essentially looking at here is, oh yeah, and so d is 0. So assuming the desired behavior was 0, right? What does our error signal do? What does this equation do as y the pre-activation goes up, right? So as y the pre-activation goes this way, the value of tan h is going to go up toward 1, right? So our error component is going to increase, but as y goes right, then the gradient of tan h is also going to go down towards 0. Okay? And so this will go to 0, and you see these two things are fighting, right? The error is going up, but that little gradient term is going towards 0. And if we erase all this stuff, right, we see that at first, while the gradient is still large, and the error, well, the gradient is still at large, right, at first, while we go to the right, the error goes up, right? But there comes this kind of critical point where the gradient starts to go down faster than the error increases, and suddenly, right, even though like the amount that our model is off is going up, even though it's getting wronger, the error signal is vanishing as y increases. Okay? And so this is sort of mirrored, I forget the word for it, right? But so this is like rotationally symmetric. It's kind of mirrored and flipped on the other side, right? Because the error as you go to the left and y goes negative, right? It's just it's the same math, right? It's just flipped. Bleh. Here is the positive half of that graph, right? So over here, the error is 0, right? Because right now, if y is 0, then the error is 0, right? We're getting the 0 that we want. As we go a little bit left, the error goes up, right? Which, I mean, makes sense, right? As our output increases, if our target was 0, our error increases, right? Then we hit that critical point, oops, where the gradient starts to go towards 0 faster than the error increases, and then afterwards, even though our pre-input is going up, and even though we're getting wronger, our error signal is going away, right? Understanding this graph is a little bit important, so if you're feeling a little bit lost, take a moment and meditate on it, because I'm going to show you a couple more of these over the course of these slides, all right? And as a reminder, this is a graph of the error half. It's a graph of our error signal, which is d minus f, where f is the activation of the pre-input, times that f prime, right, of the pre-input. So d minus activation of pre-input times f prime of pre-input, and the problem is that this thing is going to 0, right? Where tan h is flat, this term goes to 0, and that sort of extinguishes, dampens, swallows this term, even though it's growing. Okay. So, broadly speaking, this is a problem with any squashing function, right? Our error signal is going to get squashed every time it goes through a saturated unit, right? So remember, by squashing function, I just mean a function that does this, right? In these wide regions where the gradient is 0, right? Anytime our y, our pre-activation, goes out here, then the error signal is going to get reduced, right? These are regions where the error signal will get suppressed. Any sort of S-shaped curve that has these flat bits is going to have these regions of 0 where your gradient will get swallowed, right? So any S-shaped curve is going to have this problem, right? So that means there's a practical limit to how deep of a network we can build, okay? And again, so think about not only what happens way out here, right, where you're very close to 0, but even, let's say, in here, right, where your gradient is low. If you multiply if your error signal, right, is multiplied by this bit in here, by one of these values, it will be reduced significantly, but it won't be zeroed out, so your network will still learn. It will just learn slowly. But remember that if your network has several layers, it's going to get multiplied by that f prime several times, okay? So if your error starts out fairly large but keeps getting multiplied by these f prime, right, or tan h prime, of something large, it's going to keep getting reduced by this tiny little number, right? So your error signal is only going to be able to go back through a couple of layers before it's basically gone, right? And so you get this problem where networks that are more than, say, 3 layers deep and using tanh basically can't train the bottom layers, right? So if you're, let's just say, if you're 5 layers deep, your bottom 2 layers basically won't get an error signal because your error signal will have been decimated repeatedly by passing through this tanh prime. So that's how this limits the depth of a network you can build, okay? And this caused a thing called AI winter.